I'm Irving Bigio. I'm in a number of departments. I'm schizophrenic. Brain disease, isn't it? So I'm into optical tools, looking for, like a hammer looking for a nail. And one of the most powerful optical tools for imaging anisotropic tissues is optical birefringence. This is the property in tissue which is anisotropic, where in one direction of optical polarization experiences a different index of refraction than the orthogonal direction for the polarization. And you can do this experiment at home. You take a pair of polarized sunglasses, cross them so they're blocking light, and then extract the nerve from your body, put it in between, and you'll see it because it will rotate the light from the first polarized to seconds. And if you don't want to extract the nerve, then just take a piece of polyethylene or saran wrap and stretch it a little bit and put it in between. You'll see these nice patterns. So what we have here is we took the purple lines show you the directions of the optical polarizers in this microscope. We just basically removed the Dvorsky prisms from a DIC microscope, and we imaged individual axons from the sciatic nerve of a mouse. And you can see circled in the gray circles some examples of nodes around Gay, and these lines that you see are the myelin. So this is a highly anisotropic tissue, highly anisotropic structure. So if you orient it so that some part of the light is polarized this way and some polarized that way, so basically 45 degrees, it shines up very nicely. If we were to rotate it so it's parallel to one of these, it would just be dark. And we found out that we could actually see interesting things by looking at dynamically at the optical birefringence, because the electric field of the action potential itself is a strong electric field, and it actually distorts the local polarizability of the tissues in its vicinity, thereby causing a change in the static birefringence. So you can actually record optically. So this is an optical recording of the action potential propagating in a group of these axons from the sciatic nerve, where you stimulate it at one end and just look at it optically after you stimulate it. And it follows fairly much the electrical action potential that you would have seen if you had recorded this electrically. But notice what happens when you let the nerves get older and start to die. The myelin starts to become randomly clumping, and you get this really interesting effect, which has to do with neurodegenerative diseases, because a common factor in neurodegenerative diseases, at least the type that involve the white matter, like Alzheimer's, MS, CTE, etc., is that there's breakdown or loss of the structure, the anisotropy of the myelin. And what I don't show you here is that if we rotated that 90 degrees, it would not disappear, because these are now somewhat randomly and only local regions of anisotropy. And by doing that, we were able to show that the direction of the optic axis, which is something that defines the structure in terms of the optical birefringence, is radial in the myelin, solving a controversy in the literature, because there are papers in the literature that disagree on what the direction of the optic axis is. And just to show you what you can see without any labeling or any staining or anything, in a simple little grain slice, all kinds of interesting things about the direction of axons there for you with much, much less expensive instrument than a multi-photon system.